So I've got a big list of them. Yeah. Here are some of the questions, most of the questions actually from 12.4, where the cross product is used or calculated. So I'm going to pick one of these guys just to calculate the cross product. In fact, I'll just make one up just to get the ball rolling. So if you had a vector 1, 3, 2, and you had another vector v, and it was 5, -1, -2, for instance. If you wanted to calculate the cross product, which we're going to be doing a lot today, you set it up by first row ijk, right? This vector, the vector u, goes second. And this vector here, v, goes third. And then the formula is essentially so many of the I vector, subtract so many of the j vector, add so many of the k vector. And then it's quite, to me, it's very visual. So if you want to get the first one, the I, you cover up column I, just like that. And what you should see is a 2 by 2 matrix, and you get major diagonal, -6, take away minor diagonal, -2, and that ends up being what? -6 add 2, so that's -4i. If you want the middle one, can I cover that guy up? I guess I could do it a little bit more like that. Cover that one up. Major diagonal -2, take away 10. And then you do k. Major diagonal -1, take away 15. This guy is -12, but when you subtract -12, you end up adding it. And this one is -16. And in ijk notation, that's fine, but I prefer that guy.
-16.
Well caught, thank you. Are you comfortable with the process? Because it really is a process, right? It's not a formula, right? How you do a cross product. Now, that's basically what 1, 2, and 8, they just get you to calculate it with no particular reason. We'll come back to 2 later. And there's only one example of this particular thing, but if you calculate the magnitude of the cross product, so I'm going to use this guy here, right? If you calculate the magnitude of that, it's also equal to this fella. And then if you wanted to calculate this, you could actually do it by multiplying the magnitude of u times the magnitude of v times sine theta. And I'm going to use their question 10, then I'll bring that one that I covered up back to show you used in 2 different ways. So this is question 10, or at least a version of it. It's not question 10, question 9. Where are you hiding? That's not question 9 either. Again, I don't know what I've put there, but it isn't the right number. Here it is. It is 7. Yeah, it's 7. Kind of makes sense. It will go 3, 4, 5, 6, 7. So, a version of question 7. You're given a picture, and you're told that the magnitude of this vector v is 4, that the angle between them is 60 degrees, and that this guy over here, this guy here, has a magnitude of 3. And you're just being asked to calculate what the magnitude of the cross product is. So that's simply plug and chug, right? Magnitude of u, magnitude of v, times the sine of the angle in between. And since all 3 of these are given, you just basically just plug in the numbers. 3 times 4 times the sine of 60 degrees Since you have got it fresh in your mind, do you know what the exact value of the sine of 60 degrees is?
Root 3 over 2.
Correct.
That's just a guess.
No, it was the right guess. And if you know, we don't want decimal answers. So as an exact value, it is that. So if you wanted to know the magnitude of a cross product and all you knew was the length of both, right, the magnitude of them and the angle they make, you would do that. To me, that's not a very useful version of the formula. This is the guy we're talking about, this formula. If I rearrange it, I get that guy. Right? Basically, if you take this equation, divide both sides by magnitude of u and v, you get this guy. Does that guy look familiar to you?
It is the same thing as the cosine, except it is not the magnitude of UV cross product.
Mm-hmm. Do you remember the dot product formula for finding the angle in between two? Do you know you can use the cross product formula to find the angle between the two? So let's take this guy here. You see the fellow we've got here? There's u, there's v, and here is the cross product. So I'm going to use this formula to find the angle between these two vectors. Right? So what do I need to know? Well, I need to know the magnitude of u, I need to know the magnitude of v, and I need to know the magnitude of our cross product. And since I know what each of these vectors are, it shouldn't be too bad. 1 squared plus 3 squared plus 2 squared, which I believe is the square root of 14. This one's a bit bigger. 5 squared plus -1 squared plus -2 squared, which I believe is the square root of 30. And the cross product is this one. It's probably the worst looking one of the lot. It's -4 squared plus 12 squared plus -16 squared. And I'm not going to do that in my head. It's asking for trouble. 16, I had 144 plus 256, and I get 416. So if we put those values in here, we've got the square root of 416 divided by the square root of 14 and the square root of 30. And it's a bit on the big side, but never mind. So if I wanted to get theta, I should just be able to do the inverse sine of that. See what it looks like. That looks big. That looks decidedly big, but anyway, here it goes. Square root of 416. Oops. Inverse sine, there we go, of the square root of 416 divided by, put a bracket around the two guys in the bottom, square root of 14 times.
You need a
I need to be in degrees, don't I?
need parentheses after the 416.
Did I? I think I did that. Let's see. Divide, gotcha. Bracket, gotcha. Square root of 14.
After the 416, though. You need a bracket. And
Oh,
bracket.
I see it. Okay, gotcha. Thanks for catching that. I missed it. There we go. I hope I've got enough brackets here. And of course, I was in radians. We want the answer in degrees, but I can fix that pretty quickly. Just, there we go. 84.4 degrees. So there is an indirect use of the cross product. If you find the magnitude of the cross product and you divide it by the length of u and v, that expression will allow you to find the missing angle. So short recap. If I give you two vectors, if you know, with numbers and so on, are you comfortable you could calculate the cross product, which is the first question for today. If I tell you the length of the two and the angle, could you use this formula to get the magnitude? If I told you the vector u and v, which is a long-winded way of doing it, but if I told you the vector u and v, you could calculate the cross product. And once you knew these three, you could then use this version of the formula to get the angle between them. To be honest, if you two told me these two, wouldn't I probably use the dot product? Isn't that just a lot less work? Which is probably why nobody ever uses this formula. Unless you've already done part of it, you know, in part A or something. So if you've already had to do the work, you would probably use it. Any questions so far? Do we feel comfortable about what we've done up to this point? You feel good? You want me to do anything else? Or can I move on to our next situation, which is finding the area of a parallelogram? Ready to do that one? Right. Now, the formula for getting the area of a parallelogram it's equal to the magnitude of the cross product of u and v. So you got to imagine that they start off at the same point, right? But the two vectors u and v, like that. If you add in another parallel line this way and a parallel line that way, that is the parallelogram that we are finding the area of, okay? So it's made up of two sides, but that's all you need, right? Because won't this be the same length in parallel, same length in parallel? You got your guy. Now the version of that that I've got here is 10. So they add a little extra, I think. Yes, they do. Question 10 is a two-dimensional version of what I'm going to do in 3 dimensions. So I'm going to have a point A, 1, 2, -1. B is going to be 5, 1, 1. C is going to be 0, 0, 2. And finally, D, oh, change that. It has to be a parallelogram. My apologies. That would just be a random zigzag shape. Okay, there's my first one. This is my second point. That's okay. I can keep those two, but now I have to be more careful. Well, I can do anything I like actually for the third one. I should have thought about that. Only you have to be careful about the last one. Okay, so that one goes. So that goes -4 plus 1. Yeah. So I want to find the area of this parallelogram. And can you pretend that it looks like that? I'm not even going to try and do it. Nobody tries to draw things in 3D anyway, right? There's my parallelogram. A, B, C, and D. So we need a strategy, right, in order to find this fella's area. So essentially, don't I just need 2 vectors? One to be U and the other to be B. Would it make sense that A to B could be one of my vectors and A to D would be my other? Can that be my U and my V? That's it. So vector AB, you get that by, I promise not to do this formula, but since I've started it, I'll finish it. So 5 take away 1, second take away 1, second take away 1, Second, take away 1. There you go. And AD is going to be my other one. And AD is this one and this one. So second, take away 1, -5. Second, take away 1, -1. Second, take away 1, 1. So these guys are my U and my V. So second takeaway first, second takeaway first, second takeaway first. So I now find the cross product. And once I've got that, I'll then find the magnitude and we're done. So you have I, we have J, we have K. 4, -1, 2, -5, -1, and 1. So it's going to be so many I's, take away so many J's, plus so many K's. Cover it up, cover it up. -1, take away -2. Middle one, 4, take away -10. Last one, -4, take away 5. So we get the vector -1 add to that's 1, 4 out 10 is 14, then you make it negative. -4 take away 1, make it -9. There is your cross product. So we found A to B, we found A to D, did the cross product. So the area of the parallelogram is the magnitude of that vector. That one there. So it's going to be the square root of 1 squared, -14 squared, and -9 squared. Again, I'm not going to try that. It's 1, add 144 plus 81.
It's 14 squared.
Yeah, 1 plus 114 squared. Yeah, plus 81, that looks better. 278. And there's an exact value. That's correct. Guess I should check. Can you do 4 on this one? No. Can you do 9 on this one? No. Can you do 16? Nope. Can you do 25? Forget it. Can you do 36? 36. 36. No. I'm just going through all the obvious ones. 81, no. 121, no. 144, no. That's it. Can't make it any easier. That's as good as I can say it. So we're finished. So if I gave you the coordinates of 4 points, do you feel comfortable that you just pick one? I just chose A because it was the first letter in the alphabet, right? And go A to B and then go A to D. And this would represent the parallelogram. 2 vectors like my U and my V. Cross product them, magnitude, and that's what's finished.
I have a question.
Yes.
So on the J coordinate, why is there a -10?
Let me check it in case I screwed up. It's 4, take away -10.
All right. Never mind.
Yeah. And did I add it right? Yep, that's good. That's the right number. You comfortable with finding the area of a parallelogram in 3D space if all I tell you is the coordinates? If I only gave you those 3, so it's now a triangle, right? So it's basically that shape, right? So if I only gave you 3 points because I want a triangle, what would be the alteration to this answer? What would the area of?
2.
Yeah, that's all. So triangle, parallelogram, they're almost the same question, aren't they? You do the same steps. If it's a whole thing, parallelogram. If it's only like this little guy, half the parallelogram. I think that went pretty smooth. Feel good? In a way, it's a lot easier when there's no algebra involved, isn't it? Much easier when it's numbers and the answer's a number and the process involves numbers, I think. So I can chuck that off my list, chuck that off my list. They're only one of them. Right, we talked about triple products now, and that's where there's a big bunch of questions. And you're going to use triple products. That's a dot product with a cross product. Typically, the first guy dot the cross of the second two and the third, right? Those two. And here's a big bunch of questions. And the triple product can be used to prove that vectors are and why am I saying collinear? It's the wrong word. Coplanar, that's what I meant to say. To test if they're coplanar, and we can also use it to find the volume of a parallelepiped. Parallelepiped. So let's do can you prove that something is essentially lie on the same plane? So coplanar means it's always three or more vectors, but typically three. All three vectors lie in the same plane. So I want you to think of a plane as being an infinite flat piece of paper, right? Like that. If you have coplanar vectors, the vector u, the vector v, if you have them all starting from the same point, and let's say the third one, we'll call it w, they are all on that piece of paper. So you can imagine this piece of paper tilted, but you see those three green guys are all on the same piece of paper. That's what coplanar looks like. If you think about what typically happens with vectors, don't they all kind of point in their own merry way and they're really not pointing together? Coplanar is when they flatten together. You know, that look like that. You know, if I angle them, can you see them? Same plane. That's what coplanar is. Now you can imagine it's hard to test our three vectors coplanar, right? You know, or it would have been, except we've got a very easy test. Three vectors, I'll call them A, B, C, just because I want to, are coplanar if the triple product, can anybody remember from yesterday, what does the triple product equal if three vectors are coplanar?
0.
Yeah, and when we do that, we mean the zero vector, don't we, right? We don't just mean the scalar zero, but a vector 0, 0, 0, right? So they have an example of that. I'm looking at, what am I looking at? Question 12. So we are going to test coplanar. Now, it would be really nice if they just told me A, B, and C, right? Because then I could do this. But they take it like they did that earlier one, you know, the one where we had to find A to B and so on. So they're going to do that same kind of situation. We're going to find a vector u, going to find a vector v, and we're going to find a vector w. And we're being asked if these vectors are coplanar. And u is the vector AB, v is the vector AC, and w is the vector AD. So can you imagine there's a point in space called A, and there's a guy up here, B, another guy over here called C, and one down here called D. And we are going to find those vectors, and we're trying to find out, are these three vectors coplanar? Right, like they're all in the same situation. Now you need to tell me the coordinates, which they do. And so I'll just write them up here, 2, 1, 1, 3, -4, 6. 8, -2, -2, and finally D, 7, 3, -7. Okay, if I'd left enough room, which I haven't, never mind. A to B, second take away the first, 1. -4 take away 1, -5, 6 take away 1, 5. Are we comfortable with that? Second takeaway first. I want V now. That's AC. So ignore that guy. 8 take away 2, 6. -2 take away 1, -3. -2 take away 1, also -3. You comfortable with that one? W then. 7 take away 2, 5. 3 take away 1, 2. -7 take away 1, -8. Are you comfortable with all three? Looking good? Right. Now, we've got our 3 vectors like our A, B, C, but we're going to call them U, V, W because that's what the question decided to call them. And we are going to calculate U dot V cross W. In case you're concerned that you have to do them in that order, the good news is you can mix them and shuffle them any way you like, and you still get the same answer, right? So I could have said V dot U cross W. I could have said W dot V cross U. I could have done any of the combinations, right? So that's not important. Pick whatever number in the alphabet you like. Me personally, if there was any of these vectors had zeros in them, I would want it to be part of the cross product because zeros tend to make your life a little bit easier in calculations. But apart from that, I have no preference. So I'm going to do the cross product first. So I'm doing that bit first. So we have an I, we have a J, and we have a K. And this is V, and this is W. And so my cross product is going to be so many I's, take away so many J's, plus so many K's. Okay, 24, take away -6. Middle one, 40, -48, I should say, take away -15. Last one, 12, take away -15. So what do we get for the cross product? That's 30i. Can't read my own writing there. That's plus 15, but that's negative, so that's -33. 2 negatives make a plus, so it's plus 33. And this one is, I think, let's check it, 12 odd, so that's a 27k. But all those calculations look okay. If you've seen any that don't work, tell me. So I'll assume that everything is good. So 30, 33, 27, I like that. And now I'll go and do the dot product part. So U dot the cross product. U is this guy. So 1, -5, 5, dot product with 30, 33, 27. Okay. And just notice I'll have to move up a little bit more. Here we go. 1 times 30 plus -5 times 33 plus 5 times 27. That's 30. Take away 165 plus 135. Am I good or am I good? Then I said 0 as a vector and I was wrong. It's 0 as a scalar. So we're coplanar. Now, considering the number of places in that process I could have screwed up, are you not impressed, Caitlin? Right. Cam, are you not looking at that and saying, That was a fluke, right?
It was beautiful.
It was elegant. See, when you get an answer that just comes out nice like that, doesn't it make, it makes it kind of worthwhile. What you don't like is that, those questions where you keep screwing up, but then you screw up in a different place later on, so you just can't get it to work. Those are very frustrating. But that one was nice. And by the way, it's the right answer. So it means they're coplanar, right? They lie in the same plane. Those are quite big questions. Is one enough? Do you feel comfortable with one? Right? I mean, it's really just do this, do that, right?
Well, it does say
Yeah.
volume 2 there.
Oh, that's true. I'm going to do a volume one, so I'll do pretty much the same process. But when you do a volume one, you get a guy called a parallelepiped, right? What would be the volume if it was coplanar?
Just the area.
Well, it would actually be zero because it
Oh,
would
the
be a
volume is
flat
zero.
piece of paper, right?
Yeah.
So you can see the connection that if the answer is zero, they're coplanar, in which case you can't get one of these guys. They don't exist because it flattens down to 2D. It's, the volume of a flat piece of paper is zero. Isn't the area of a straight line zero, right? It's like when you move down one dimension, you lose whatever it is you were calculating, right? A volume disappears when it goes 2D on you. Unless you're a black hole, which for some reason, laws of physics seem to go weird. Right, let's find a parallelepiped one. Quite a lot of the coplanars. Here's one. Do they keep having to do that? Can I get one where I don't have to do coordinates? No, okay, I have to do coordinates, so might as well live with it. Question 16. You have a point P with coordinates, that guy. You have a guy Q with those coordinates. You have a guy R, and that's the coordinates, and you have a last guy S, and you get that. And it says, find the parallelepiped that uses PQ, PR, and PS as its vectors. Now, I can imagine this is PQ going this way, R going that way, and S going that way. I'm not sure if I'm even going to be successful here. Yeah, it's a mess. Can you trust me? It's a parallelepiped. It's a three-dimensional parallelogram based on the fact that you're starting at one point and going in three totally different directions. Wouldn't that be like the corner of the shape? That's really all you need to create. So in this case, let's find out who they are equal to. 2 take away -2 gets you 4. 2 take away 1 gets you 1. 2 take away 0 gets me 0. That's the first one. PR. 1 take away -2. 4 take away 1. And -1 take away 0. I don't like this last answer. 2 take away 0 is 2. Yeah, I like it now. And last but not least, PS. 3 take away that guy is 5. 6 take away that guy is 5. And 2 take away that guy gets me 2. So quick check. 4's good, 1's good, 2's good. Happy now. 3's good, 3's good. Yep. PS now. 5's good, 5's good, 2's good. Okay, I'm comfortable with those guys now. So these are basically the 3 vectors that I drew, right? It doesn't matter who you make the first and who you make the other 2, right? Since none of them have got zeros, I don't think it matters. So I'm just going to do them in order. And the volume then is the triple product, the first one, and the cross product of the other 2. Oh, before we finish this question, it might happen, I guess 50% of the time it probably will happen, that this number, and it will be a number, right, ends up being negative 42 or something. If I do get a negative number, what will be the volume of my parallelepiped be?
Negative.
Absolute
No.
value.
Just make it an absolute value, right? Just make it positive, right? Of course, if you get the answer 0, doesn't it mean that this shape is coplanar? And you should then complain to WebAssign, why did you ask me a question that's, you know, not viable, right? But I strongly suspect that's not going to be the case. So cross product, let's do that first. You are going to, you think, or if you do think that after this section, that's the end of cross products, you're wrong. They're coming back, right? So the next section, you're going to get some more of them. But PR is this one. So 3, 3, -1, and PS underneath that, 5, 5, and 2. So we'll do this cross product. So many i's, take away so many j's, plus so many k's. Okay, 6, take away -5. Middle one, forget that. 6, oh, interesting, take away -5. Last one, 15, take away 15, 0. So you get 11, that's that one. That's 11, but you make it negative, and that guy's 0. So that's the cross product. Interesting. Now we will do the volume. The volume is PQ dot product with this cross product there. It's 4, 1, 2 dot product with 11, -11, 0. So you'll get 4 times 11 plus 1 times -11 plus 2 times 0. That's 44 take away 11, add 0, and that ends up being 33. So I don't need to fix anything. And yeah, it's the right answer. We cool? It's all number crunching. I think we should be pretty good at cross products now, right? We've done them for different reasons, but it's the same cross product every time you do it, right? It's the same process. Any questions? So if I give you 3 vectors, can you tell me if they're coplanar? If I give you 3 vectors, can you find the volume of the parallelepiped? If I make it hard for you and tell you the coordinates first, can you still do those 2 things? So can we just call this one, stick a fork in it and call it done then? Okay. And we are finished with 12.4. So we're on to 12.5. And 12.5 is finding the equation of a line and a plane in 3D space. And we're going to start by focusing only on the equation of a line in 3D space. Oh, no, we won't. Come back. I've missed out a chunk of questions and I still haven't shown you how to do them. So let me do calculating cross products using I, J, and K. In case you need some reminding, these are sometimes called basis vectors. I is the vector going 1 in the x direction. J is the vector going 1 in the y direction, and k is the vector where you go 1 in the z direction. And we are going to look at the cross product of any one of these with any one of the other two, right? And then we're going to put them all together and do a little kind of algebra. So I'm going to tell you the first one. Well, I'll give you a chance to guess it. What would the cross product of I cross J get you? What do you think it should get you?
0.
Would be 0.
Oh. Are you still thinking triple products?
1.
Isn't a cross product, right, a vector that's orthogonal to the two that's there? Which one is orthogonal to the x and the y axis?
90.
Well, what vector?
What?
Imagine that's I, which it is, and imagine that's J, which it is, right? Because that's the x-axis and y-axis. What would the cross product be?
1, 1, 0.
Yeah. It would be k. That makes sense? 1 in the z direction. Okay. So the cross product, remember, I know we've done a whole load of calculations and we end up with numbers, but you got to remember a cross product is itself a vector, right? You only get a number when you find its magnitude, or if you do it as part of a triple product, right? Then it becomes a number, right? So that's, I suspect why you're calling it 0 sometimes. But right now, it's that guy. Now, there's a little triangle you can use to help you remember what the answer is. And on this triangle, you put an I, then you put a J, and then you put a K, right? These three guys. And the way it works is I cross J gets me K, right? I cross J gets me K. Do you notice? Now, what would J cross K get me?
I.
Okay. That makes sense? What would, what's left? What would K cross I get you?
Yeah.
Put the So that makes sense now that any two would get you the third one, right? Now, we know enough about cross products to know that the order is important. Done it. What would, what would J cross I get you?
Negative K.
So if you want to use this little triangle, if you follow the arrow, the answer is positive. If you go against the arrow, the answer is negative. So if somebody said do J cross I, you would say J cross I. To see you're following, you're going opposite, right? J cross I gets you. Okay. Okay. Right. J cross I gets you K. So what that allows us to do is if we can memorize or use this little guy, we can actually do combinations of I, J, and K, any two that you like, cross product, right? Now, what do you think I cross I gets you?
I squared.
You could call it I squared. It's not called that, but you could call it that. But what is it equal to as a specific vector? And of course, if you've never done this, this is brand new, but maybe you can have a good and inspired guess at what you would get. Now, if you think about what a cross product does, that might help. It gives you a vector that's perpendicular to I and I. Well, in other words, you don't have really two vectors. Don't you have the same vector on top of itself? So what do you think you might get out of a situation where you do a cross product with another vector that's really the same as it? Last chance. You get the zero
Maybe.
vector. You get a zero vector. You can try it out, you know, do that guy cross product with himself. The answer is 0 every time. Well, if you've got all these IJKs and so on, you can then do questions like questions 3 to 6. Let's pick some of them and see how they go, because they're pretty quick once you know what you're being asked to do. So in here somewhere. Okay, that's 5, there's 4, there's 3. So if you were being asked to find I cross J cross K, right? You want to find out the answer to that. What, using my little triangle, what's I cross J going to get you?
K.
And what does K cross K get you?
0 vector.
So you have now got your first answer, right? Now, if you stick in numbers and you can do essentially the distributive law in vectors, a kind of pseudo distributive law with a cross product, you can also do a pseudo version of FOIL using this. So if I, for instance, told you 3K cross product, I take away 3J. Think of a distributive property, right? Think like multiplying out brackets. So you'd get 3K times I, right? That'd be essentially that guy. And then this guy cross product with this one would get you negative 15K cross J. You still with me? 3K times that gets you 3K cross I. 3K cross this gets you, well, the numbers can just, why did I do that? Gets you that number, right? Now, what does K cross I get you?
J.
What kind of J?
3J.
What kind of sign?
Positive.
So you're looking at that one down there?
Yeah.
Good. Let's forget about the -9, right? I should be clearer with my questions. What does K cross J get you?
Negative I.
And so won't that get you -9 negative i's? So maybe I should put that in. And so you get 3J plus 9i. Now, if you did a complete vector, do you know how you would get a vector like A is, 1, 3, 2, right? And B is like, 4, 1, 7. If you did the cross product of that, what you could do is call that 1i, 3j, 2k, 4i, 1j, 7k, and do calculations like this, which would be horrendously ugly. But if you did it, you'd get the cross product. And it might even explain why that guy in the middle's got a minus. Right? Why is it plus the first one, minus the second, and plus the last? Now, I promised you that you can also do essentially a distributive law. Think FOIL. 2i cross 2i. So 2i cross 2i. 2i and that one. So that's going to get you 2 and 3. That's going to get you 6i cross k. Probably should have done them while I was at it. Right. You go this one, you're going to get 4j cross i's. If you do this last one, you're going to get 6j cross k, right? So 1, 2, 3, 4, right? Essentially FOIL. Have you noticed that you kind of write down the cross rather than just say AB or that, right? You write down the cross. Now, this guy is 4, but what does I cross I get you?
0.
0 vector. So isn't 4 times the 0 vector just a 0 vector? In other words, it's not going to make any contribution. Now, what about this fella here? I cross K. What does
Negative
I?
J.
Okay, so that's going to get you -6 J's. What's J cross I going to get you?
Negative 4K.
And what's J cross K going to get you?
6I.
That one there. And we're basically finished, but I would do the I's first, the J's second, and the K's last. So one of the, I'm making this up because I don't know for sure, but I think one of the reasons why IJK notation is liked in some places is, isn't this much more like algebra, distributive rule, and foiling than that table I just gave you, right, where you write down IJK and cover things up. So it's got its advantages. But that's it. We definitely are finished. There's a question at the top, number 1, but really it's just yeses and nos, and I think it's much more fun if you just try it out yourselves. So equations of lines and planes, as I said, we're only going to focus on the first one. So I'll start that again. Finding the equation of a line in 3D. And it's not as, I don't know if you think it's easy or not, but it's not as easy as you think to describe a line, right? An infinite line in 3D space. Now, if I was doing a line in 2D space, wouldn't I just say y equals 2x plus 3, right? That's what a line in 2D space looks like. I mean, I could rearrange it, couldn't I? Say 2x take away y is -3, which would be the equivalent to it, right? But it's a combination of x's and y's. Now, you might think, well, the equation of a line, let's put 1 in. Can you imagine this is the line, call it L1, right? And it's sticking out of the paper like this pen, right? That's the line. So I want to find some way of representing every point on that line in 3D space, right? Because it goes on forever. It's not a vector, it's a continuous line, right? A vector has a start and a finish, right? A line has no start or finish, right? Continues forever. So you might think, does it end up looking like that? Well, no. If you do all the points that look like that, you actually get a plane, right? A flat piece of paper, not a line. So we have to figure out how to describe the equation of a plane. And there are 3 different methods for telling people all the points that lie in that red line. Okay, so let's kind of take you how it works. First, you need 2 pieces of information. The first thing you need to know is a point on the line. Any point will do. In this case, I'm telling you the point 135. The second piece of information you need is called a direction vector. And the direction vector very often is called V. And essentially what the direction vector does is it just tells you what direction the line goes. So you give me a vector and you say, start here and go in the direction 1, 2, 7, right? And with those two pieces of information, you've actually described the line in 3D space. Can you imagine if I tell you, here's a point, and then just go that way forever, right? Go in the direction of, 2, 4, 6, whatever it is. Let's suppose it's in the direction -2, 1, -3, for example. With only those two pieces of information, you can create the equation of the line, and you can do it as a parametric, you can do it as a vector, and you can also do the equation of the line in a form called symmetric. Okay, now I'm coming back to that one. Let's show you the general version. You're told any point on the line. So let's call it x1, y1, z1. And you're given a direction to travel. So the direction vector v, and I'm going to call the direction vector v, what will I call it? ABC, I think. A, B, C. Then the equation of the line, let's do parametric form. Is x equals x1 plus AT, y equals y1 plus BT, and the z coordinate is z1 plus CT. So in my question here, the parametric equation of this line will be as follows. 1 minus 2t, 3 plus 1t, and 5 minus 3t. So if you find all the points in 3D space that have an x coordinate is 1 take away 2t, y is this, and z is that guy. So you might think, what's this new variable called t? T is, do you know the parametric equation stuff, right? It's just a way of representing a point in 3D space. T very often is time, so it kind of tells you where along the line. So you can imagine something just traveling along a line forever. At t equals 0, it's here, actually. And then at t equals 1, it's here, and t equals 10, it's here, and so on forever. You can even put negative numbers where you find out where it is down this side. And we call that the parametric form. Now, said there are 3 ways to describe the equation of a line, and that's just the first one of our 3. The next one we're going to show you is the vector equation. And the vector equation of a line is basically you tell me a point and you tell me this vector. And we describe it using this interesting notation, R of t. Now, do you see the little arrow above that? That's because this is what's called a vector function. And R of t will equal this guy plus t times b. So in my case, x1, y1, and z1 is essentially the position vector. That just means the coordinates written down as a vector. So that's the vector you would get if you did the origin to that point. So in this case, it's 1, 3, 5, plus t times this guy. And that's called the vector equation, the vector form of a straight line. So if you wanted to know a point on a straight line, and I gave it to you in this version, if you plug t equals 1, you will get a vector, but a very special vector, right? It's called a position vector. So if the answer ends up being 1, 2, 3, right, that means it's at location from the origin, 1, 2, 3. Right? It's really a disguised coordinate system. So we've got a really cool guy called a position vector. Maybe I should put that up here. Position vector of, say, the point P is the vector x1, y1, z1. Do you see it's the same numbers but written down as a vector rather than a coordinate? So this idea of position vector is quite helpful. Now those two are very, very similar looking. And the third and final way of writing down the equation of a line is called the symmetric form. And this doesn't look like any of the other two. It's x take away x1 over a equals y take away y1 over b equals z take away z1 over c. And to remind you, that's x1, that's a, that's y1, that's b, that's z1, and that's c. And that guy is the equation of a line in 3D space written in what's called its symmetric form. Now, all three of them are telling you the same thing. Parametric form, vector form, symmetric form. Now, one of the things you might want to do is, how do I take an equation that's written in symmetric form and make it parametric, right? How do I take this guy and turn him into him? Or how do I take this guy and turn him into him, right? How do I convert from one to the other? Because if I
Algebra.
can't, yeah, it's going to be algebra. If you can't do it, then they're not really equivalent, or at least there's no easy way to tell. Let's go this way. How do you think I could turn this into that? Any ideas how you could turn these three equal to each other into x, y, and z so it looks
Equals
like
t.
this? You do. So you make the thing equal to t. Now, if you take each one in turn and you make them equal to t, you'll get it. So let's take that one. If you take that guy and say it's equal to t, a little cross multiply, and then you add one. You see how it works? Now, suppose I want to do the second one. Little cross multiply, add 3. Right, Z would work the same way. Okay, so if you want to take symmetric form and convert it into parametric, you take the thing and you make it equal to t, and you take one piece at a time and solve for x, y, and z, and you've got it. How do you go the other way? How do you take a parametric and make it into symmetric form, right? So how do we get from here to the guy that looks like that?
You
Solve for
set
t.
up to t, but you do the reverse, right?
Yeah. So you take each question, right, each piece, and you make it solve for t. So for instance, if I did x, which is this guy, if you take away 1 from both sides, and then you divide both sides by -2, do you see I've got the first one? You see it? Now, how do we get then from these two guys to vector form? Well, if you want to go from this guy to that guy, right, from this to that, can't you just basically separate out that as a vector, separate this as a vector, and stick t in the front? Would you agree it's pretty quick? Vector, vector, stick a t at the front. Now, if you want to go the other way, right, if you want to do this fella and turn him into that, can't you just say 1 minus 2t, that's the x value, 3 plus t, that's the y value, and 5 take away 3t, that's the z value. Can't you just combine this into a single vector and then say the x component, the y component, and the z component? If you wanted to turn this guy into that or vice versa, I suggest strongly that you turn them into this guy first, and then it's easier to convert, right? So if I wanted this, I would turn it into parametric. I'd then take the parametric and turn it into that. It's a little bit longer, but it has a flow to it, I think, that makes it easier. Okay, that's a fair amount to take in one go. Have we got any questions before we actually start doing some questions? Okay.
Anybody hear a joke?
Yeah, we could do with the joke. Give me your
Oh,
joke.
man.
Do you have one? And is it suitable?
Well, when you're saying u, talking about the u vector,
Yes.
it reminded me of a joke. So there was a kid went to school and he got to say something. And he said, I is, and the teacher said, no, 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 it's I am. And the boy said, okay, I am the 9th letter of the alphabet.
That's it. Okay. Jessica, if I bar him, will you back me up that he deserved it?
Sure.
Aw.
Okay.
No.
No? Okay, you're too nice.
I don't know.
That was horrible. That was so bad, Jeremy. You should be shot. Well, not physically shot. That's not what I meant. Okay, here goes. Question 2. Find the equation of a line that passes through the point, I like to put P in it, even if they don't, 2, 2, 3, and right, it's parallel, which is an interesting way of phrasing it. It's parallel to the vector. And I'm doing it the way I like vectors to be written. That one. Right, it's the same guy. That basically is what we would call the direction vector. Even if they don't call it that, that's essentially who that guy is, right? Because if you have a point and you go in the direction parallel to somebody, isn't that your direction vector, right? So they just disguised it by not calling it that. They just said parallel to the vector, but it means direction vector. And they want the answer in vector and parametric. Okay, so let's do the vector form. Now you take this guy who is 2, 2, 3, and you add t times that guy. If you get it, it's pretty easy to do. If you tell me the things I need, isn't it just write them down? Right? Position vector of p, t times the direction vector. Now you can combine them a little bit, and you get this guy, you get this guy, and you get that guy. That's also the vector equation, because it's a vector, right? Almost no question there at all. Now, if you want it as parametric, well, since I've written it this way, the parametric is kind of trivial. That's parametric. And that guy there is the vector form. Are we okay? Now, WebAssign. WebAssign doesn't want you to write it like that. I wish they would. You know, it's 3 boxes, you know, x equals, y equals, z equals. This is how you write it down in WebAssign.
Parentheses or vector?
These are they're already printed, so you just fill in the bits.
Okay.
Okay, I guess the software's not clever, but I mean, how hard would it be just to give you 3 boxes, right? I mean, it wouldn't be the worst piece of programming in the world, but that's how you write it. And the vector format, well, you just write it like that and you're fine. I hope it is clever enough to write that version, because that's also correct. Way back in Math 94, you may have got a question, find the equation of the line joining 2 points. Can you remember a question like that? Let's do it today. Let's have find the equation of the line joining 1, 3, 4 to 1, -2, 1, right? So can you imagine that's A and this is B? So the line they're talking about, doesn't it continue forever? Right. And let's find the equation of that line. I don't really care if it's parametric or vector. Once you've got one, can't you turn it into the other two anyway? So you can worry about which version of the answer do you want after that. So I need only 2 things. I need a point on the line. And I need a direction vector. Okay, I have 2 candidates. Isn't that point on the line and isn't that point on the line? Agreed? For no other reason except this one is first, I'm going to pick that as my point. Does that seem reasonable? Any point will do. And then I'll tell you at the end of this something really weird. Now the direction vector, right? Don't I need a direction for this line to travel? What do you think the direction vector is going to be?
That's the second one, to subtract the first one, right?
Yeah, so I'm going to find the vector AB. Does that make sense? Second one, take away the first one, right? And that's going to be 1 take away 1 is 0, -2 take away 3, and 1 take away 4. So there is my direction vector. Now, you put these together, the parametric equation is 1, well, technically plus nothing t, I'll fix that in a minute, -2 minus 5t, and z is 1 minus 3t. Nobody ever writes 0t. Would you agree that it's kind of redundant? You don't need it. There is your equation, right?
Is it possible to do the way around?
What, BA?
BA, and then you pick your point in of the line is B.
Yeah. Do you know you can also pick a point on the line B, but still use this vector? Right. Which is the crazy thing I kind of mentioned at the end. Do you know in 2D space, isn't y equal 3x plus 1 and y minus 3x equals 1? Aren't they all the same line? And although you might write them differently, don't they end up with a little bit of algebra looking the same? In other words, the equation of a line in 2-dimensional space is unique, right? There's only one equation for every line in 2D space. There is an infinite number, technically at least, there's an infinite number of correct answers to the equation of a line in 3D space. If I chose A, we get this answer. If I chosen B but kept everything the same, wouldn't this be a 1? Where is the guy I picked? Did I pick B? I did. I actually picked B. Okay. If I picked A, then wouldn't it be 1, 3, and 4 that would go here? Do you know the direction vector that I've got, which is this one? If I went the other way around, wouldn't it be 0, 5, 3? Wouldn't that make these numbers positive, not negative? Since it is a direction vector, couldn't I just double the numbers and would it still be the same direction? Couldn't I half it and it's still being the same? Do you see what I'm getting at? There is an infinite number of different versions of the same straight line.
So you're saying we can write whatever we want and it'll be fine?
No, because WebAssign is not clever enough to do them. So I broke my own rule here. Pick the first guy, whatever the first letter is the guy that goes here, right? And go from A to B when you do direction vector. And that will probably save you, because that's how I expect WebAssign will have approached this question. Because if you start playing about with it, there's a good chance that WebAssign won't recognize your answer as one of the infinite number of answers that could be there. Right? Which kind of, if you think about it, makes sense, because how could it ever know an infinite number of answers? It doesn't mean you can just randomly pick numbers and that will be the line. There's an infinite number of real correct answers. There's also an infinite number of totally wrong answers, right, that have nothing to do with that straight line. So I think that's kind of interesting, just that uniqueness is gone. While we're at that, just to finish off on the equation of a line, in 2D space, right, you've got this, and in 3D space, you've got, say, this guy, right? Well, firstly, they look quite different. But here's another couple of things that disappear when you go into 3D space. The slope of the line has no meaning. Now, you might think, well, that line is steeper than this red line, right? Can you imagine what I'm saying here? That blue pen is steeper than that red pen. And the reason you probably come to that conclusion is, isn't the blue one going higher quicker in the Z direction, right? So you might think that this line has a slope and that line's got a slope. But in 3D space, none of the axes, X, Y, or Z, is any more or less important than the other two.